Morning students, welcome back to Mathematics Online class. Today we are going to discuss the new concept, that is relations and functions. It is first chapter from second PUC, right? So relations and functions. Relations and functions. Morning students, welcome back to Mathematics Online class. Today we are going to discuss the concept of relations and functions, which is first chapter from the second PUC. First chapter from the second PUC. So relations and functions. Relations and functions. See, already you have idea about the relations and functions in the first PUC, because already you studied what is meant by relation, right? What is the definition of relation? From that, how to find the domain and range of the particular relations, domain of the relation, right? And also functions, types of functions and their graphs, different types of functions and their graphs, like identity function, constant function, modulus function, signum function, greatest integer function, their domains and graphs. So in this session, we are going to discuss the types of relations and various types of functions, and also invertible function, composition of functions, and also binary operations. Before that, first we have to know what is meant by relation, right? Once again, we have to know what is meant by relation. First of all, we have to write the definition, each and every definition in your book. What is meant by relations? Relation means what? So here, a relation definition. First, we have to write the definition. A relation, capital R, from a non-empty set, capital A to non-empty set, capital B is a relation capital R from set A to set B is a subset of Cartesian product. Already you know the Cartesian product of two sets that studied in the first PUC. So a relation capital R from a non-empty set capital A to non-empty set B is a subset of Cartesian product of A cross B. That means relation means what? Subset of Cartesian product of two sets. That means here we define the relation capital R is, we represent like this one, capital R relation, any relation is subset or equal to the Cartesian product of two non-empty sets A cross B. Here A and B are non-empty sets. Right? This is the definition of relation. So Cartesian product, you know that by taking two sets, when we have to write the Cartesian product of two sets, for example, see here. So here set A is 1, 2, 3, set B is 4, 5, 6. Whenever you want to write the Cartesian product, not relation one, we write here Cartesian product. A cross B means all possible ordered ways. All possible ordered ways is called the Cartesian product. So here 1, 4, 1, 5, 2, 6. Sorry, 1, 5, 1 6 2 4 2 5 2 6 3 4 3 5 3 6. By writing all possible ordered pairs from A to B is called a Cartesian product, right? So in that relation is one condition. Here they give one condition in the problem. Relation is the subset of Cartesian products. Subsets of Cartesian product, right? Then here, what is domain and range of the relation now? Domain and range. What is mean by domain and range of the relation? First of all, domain of relation is domain of any relation is equal to all first elements of the relation, all x coordinates in ordered base, all x coordinates, all x values, all first set values are called the domain of the function. We can write in circular form like this: small a belongs to capital A, small a belongs to capital A comma B belongs to relation for all a small a belongs to capital A, set A. So this is called the domain of the function, where ordered A belongs to relation for all B small b belongs to capital B set. This is the Cartesian product. In case if you want to take any relation, for example, they define the relation like this now. So set A is 1 2 3, set A is 1 2 3, right here. Then relation is x plus y is equal to 4. X plus y is equal to 4, where x comma y belongs to set A. This is one relation. This is the Cartesian product. This is the relation. See, x plus y is equal to 4. Possibilities is one relation by taking a to a. So here x value is 1. By taking y value is 3, it is 1 possible. Then after that, by taking one combination 1 3, then 2 2 2. Next 3 1. So this is the relations from A to, for example, which satisfies the relation x plus y is equal to 4. X plus y is equal to 4. Right. So this is one relation. In that domain is what? Domain means all x values. 1 2 3 is the domain. 1 2 3 is the domain. Then range is what? Range means all y coordinate values 3 2 1. Here also 1 2 3 is the range. Right. So here range of the relation is equal to B small b belongs to capital B such that A comma B belongs to relation for all small a belongs to capital A. So these two conditions define the domain of the relation and range of the relation. Clear? So and also here you remember one more condition: the number of possible relations from A to B. For example, if set A has m elements, set B has n elements respectively. Then possible relations from A to B. Possible relations is equal to 2 to the power of m into n. This is the formula. Number of relations from A to B. Then A has m elements and B has n elements. Both are non-empty sets. Then that is 2 to the power of mn. Here we define the relation from A to A. A relation defined on A to A. So here is 1 to 3. Here is 1 to 3. Here we define the relation like this. The relation is x plus y is equal to 4. Then possibilities 1 3 2 2 3 1. Right. where x ordinates, first values are called the domain of the function, then all y ordinates are called the range of the relation. Sorry, relation, range of the relation. Clear? Next, this is the relation condition. Remember it. Just what is the definition of relation? Then relation is nothing but subset of the Cartesian product. Subset or equal to the Cartesian product. In that relation, whenever we define the relation, all x ordinates are called the domain of the relation, all y ordinates are called the range of the relation. Then what is meant by codomain? Codomain is nothing but all elements of set B. All elements of set B. Right? Range is different, codomain is different. Range is always subset or equal to the codomain. Range is always subset or equal to the codomain. Clear? Next, these are conditions we know that in first PUC. Now, say based on this, now we have to discuss the types of relations. Types of relations. Right? First of all, see here. Types of relations, very important concept for 3 marks. Types of relations. First one, types of relations. Types of relations. Types of relations. In that, first one is empty relation. Empty relation. Empty relation. What is meant by empty relation? See here. First we have to write the definitions. Definitions also important for 1 mark. That's why first we have to write the definition and also we have to learn it. What is meant by empty relation means empty. There is no element. Right? Empty relation. So here. Then what is the condition here? See, a relation capital R. That means we define the relation capital R. Relation we represent with capital letters. So we define relations for any two sets sometimes. For example, A comma B belongs to relation. Sometimes we represent like this one. This order pair belongs to the relation. Or otherwise, this order pair we can represent A related to B. A related to B also. Capital R. Right. But like that also we can represent the relations. A related to B. Right. Here see that a relation or in set A. In set A. So we define the relation in set A. That means what? Whenever we don't want to define the relation, there must be required the set A. Relation define ಮಾಡ್ಬೇಕಂದ್ರೆ ಕಂಪಲ್ಸರಿ ಒಂದು ಸೆಟ್ ಇರಬೇಕಲ್ಲ ರೈಟ್ ಸೊ a relation or in set A right is called empty relation. When that set A is called empty relation, set A is called empty relation. Empty relation, no element if no element of set A is related to any element of set A. See, no element of set A is related to any element of set A. That means what? Set A alire element A element alli mapping agala. So why set elements are called the images of set A, right? Here no element of set A is related to any element of set A. That means here we write the relation capital R is equal to empty relation when we take the subset of A cross A. So by taking A cross A, Cartesian product of A cross A, Cartesian product of A to A, no element is related to this set. No element is related to the relation. Right? For example, see one example. See the example. Here, phi is subset or equal to a cross e. Right? Here, one example. For example, here set A is 1 to 3. Set A is 1 to 3. But here we define set A to set A. For example, set A to set A means here we write the definition from A to A. We have to consider set A is different and set B is different also, right? For example, set A is 1 to 3, set B is 4, 5, 6. 4, 5, 6. I write one example for empty relation. See this example. If relation in set A 1 to 3, B 4, 5, 6. Capital relation is equal to x comma y such that x greater than y. X greater than y. Where x comma y belongs to the x comma y belongs to the set x belongs to set A, x belongs to set A, and y belongs to the set B. This relation is defined by here. Once we have to observe relation on set A 1 2 3 B 4 5 6. Capital R is equal to such that capital R is equal to x comma y such that x greater than y, x greater than y. This is the relation. This is the relation where x belongs to set A, y belongs to set B. Okay. Now, what for this relation, is there any ordered pairs are possible? For this relation, is there any ordered pairs are possible? See, here 1 2 3 is there in first set. In second set, 4 5 6 is there. We define the relation from A to B, which is x greater than y. Right? The x value there is stated. Is there any chance? No. That's why here for this relation there is no ordered pair. That's why R is equal to null set. R is equal to null set. This is the example of the empty relation. This is the example of empty relation mode. Right. The second one is universal relation. Universal relation. Universal relation. What is meant by universal relation? See, universal relation means a relation capital R in set A is a relation capital R in set A is said to be is called or is said to be is called universal relation. Universal relation. Universal relation if every element of set A is related to 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 all elements of set B. Every element of set A is related to all elements of set A, all elements of set A. For example, here we define set A to set A mode. Condition: every element of set A is related to all elements of set A. Right. This is the example of universal set. That means its relation we can write as capital R is equal to A cross A, because we are taking all possible ordered pairs. Cartesian product represents the universal relation. Right? So here one example also is there in textbook. We will discuss. Say these two both note here. You have to remember the note. Both empty relation and universal relations. Empty relation and universal relation or rival relations. Rival relations. Sometimes both empty relations and universal relations are sometimes rival relations. Right. So both are rival relations sometimes. See, for these two conditions, they give one example in textbook. Textbook based on empty relation and universal relation. Right. See that example. See that example here in textbook. Check it out. Like, see the example. See the example. Here, see the example. Example 1. Here, example 1 related to the universal relation and the empty relation. See the example. Let capital A be the set of all students of a boys' school. Capital A be the set of all students of a boys' school. Show that the relation or in A, capital A, given by capital R is equal to A comma B, such that A is a sister of B is the empty relation, and R dash A comma B such that the difference between the heights of A and B is less than 3 meters is inversal relation. So here they given one question mark. Here, what is the given question here? Let capital A be the set of all students of a boys' school. Here, given that, see the solution directly here. Let capital A be the set of all students, set of all students of a boys' school. That means what my here represents what capital A be the set of all students of a boys' school. Capital A be the set of all students of a boys' school. So here all students are boys only. But here they are asking the relation. Relation in the first case A comma B such that A is sister of B. A is sister of B. A is sister of B. So here they define the relation A comma B such that A is sister of B. Is it possible the condition? See, A is sister of B. Here in set A, set of students is all boys. Set of students are boys. Here they define the relation. Set of students in set A all boys. In set B also. Here in both cases boys only. Here boy 1, boy 2, and so on boy n. Here also boy 1, boy 2, boy 3, and so on boys n. Here they define the relation. Right. A to A. Then they are asking the condition A comma B. You should take any ordered way. A is sister of B. Is there any chance? No. So here A is sister of B is not possible because A and B, two students are boys only. That's why here R is equal to null set. R is null set because A and B both are boys. That's why A is not a sister of B. So this is our null set. So this is one example of the empty relation. This is one example of the empty relation. Similarly, for universal relation, the given condition or dash is equal to A comma B. Here set A is the set of all students of boys school, right? Or dash is A comma B such that here the relation condition is the difference between heights of A and B is the difference between heights of A and B is less than 3 meters, less than 3 meters. It represents the example of universal set. This is example of empty relation. This is the example of universal relation. See, we should take A comma B. The difference between heights of A and B is less than 3 meters. For example, if you take here relation, first two boy one, two boys, or B1 B2, or B1 BN, or boy N and boy 1, or otherwise boy N and boy N. If you take any condition and so on, the difference between heights of A and B is less than 3 meters. Less than 3 meters. Here, for example, if you take A, B, both are boy 1 means their difference is 0. Height of their difference is 0 meters. Similarly, if you take any boy mode, it's not possible to more than 3 meters. Their differences. That's why here, if you take any ordered way, then it must be satisfies this relation, the difference between height of A and B. That's why here R dash is equal to A cross A. That's why it is a universal relation. Right. So this is the example of empty relation. This is the example of universal relation. By taking any ordered pair, not possible any student is more than 3 meters. Same class students, not less than 3 meters. 3 meters. Right. Next question. Next. So they given these conditions. One is empty relation, after that universal relation, then after that the reflexive, symmetric, and transitive. Right. Identity relation also is there, but here we discuss the reflexive and symmetric relations. One of the most important condition: reflexive, symmetric, and transitive. Because when the relation satisfies these three conditions, that is called a equivalence relation. Most important condition is equivalence relation in the relations. So now next one is third condition, third definition. In that, first one is reflexive relation. What is meant by reflexive relation? Observe carefully. Reflexive relation means what? Reflexive relation. Here also a relation capital R from in set A. If A comma A belongs to relation. If A comma A belongs to the relation, for all this small a belongs to the set A. This is the definition of reflexive relation. Reflexive relation means relation in set A where small a comma a belongs to capital R. That means taking two elements that must satisfy the relation. Same element must be in the relation, that is called a reflexive relation. For example, here which type of example is there? For example, here example, if you observe example, a on relation in set A is equal to 1 to 3. 1 to 3. 1 to 3. See, reflexive relation, when it is called reflexive relation, we define the relation in set A. Right? Here, we write the relation like this. When you write the relation like this, 1 1, 1 2, sorry, 1 1, 2 2, 3 3. Or see the examples from here. This is the first one. Right. Second one is R is equal to 1 1, 2 2, 3 3, then 1 2, 1 3. Right. Then C is R is equal to 1 1, 2 2. Right. Like this is there. For example, we define the relation on set A 1 to 3. It is the relations. Some possible relations is there. Here we are observing example. Right. Once observe the example here. See, when we define the relation in set A 1 to 3, what is the reflexive condition now? A comma A belongs to capital R. That means all doublets. Simply we have to take all doublets. For example, if you take one element 1, that must 1 comma 1 must be related to the relation. 1 comma 1 must be in relation. Then that is called the reflexive. Not only 1 comma 1, all elements of set A. For example, here 1 2 3 is there, means must have shift 1 1, 2 2, 3 3. 1 1, 2 2, 3 3 is there in the relation. That relation is called the reflexive relation. Right. So remaining conditions no need. When all elements A comma A belongs to capital R, then that is called the reflexive relation. For example, here we have to observe. Here set A is 1 to 3. Set A is important for this questions. All questions when we define the relation, must and should be required the set A or set A. One set is required. Set of elements. Right. Here 1 1, 2 2, 3 3 is there. Right. So here 1 2 3. So 1 1, 2 2, 3 3 is there. That's why it is reflexive. Here observe this one. Second example. 1 1, 2 2, 3 3. All is there. And also extra 1 1 2, 1 3 also is there. Possible for some other cases also possible. Not only doublets there is. Other cases also possible. So whatever the conditions now, but you require A comma A belongs to R. That means 1 comma 1, 2 comma 2, 3 comma 3 is there, means that is reflexive. So these conditions are mandatory, compulsory. The remaining are optional for reflexive. Now we are discussing reflexive relation. Clear? So here this is also reflexive relation. Then see this condition once you have observed. Here doublets is there 1 1 2 2, but 3 3 is there. No. So ಇಲ್ಲಿ 3 3 ಇಲ್ಲ ಮಾಡಿ compulsory ಇರಬೇಕು 3 3 అనేది ಕೂಡ. Then only it is reflexive. That's why it is not a reflexive. Clear? Reflexive ಅಂದ್ರೆ ಏನು ಅರ್ಥ ಇದೆ? So all A comma A belongs to R, then only it is called the reflexive relation. That is some example problems is there. At the time of problems we will discuss. Right. So this is the definition of reflexive relation. After that, symmetric relation. Second one is symmetric relation. Symmetric relation. What is meant by symmetric relation? Right. See here. Then a relation capital R in set A. A relation capital R in set A if the condition for symmetric what means A comma B belongs to R. Already one ordered pair irutte A comma B belongs to R and ordered pair irutte relationally. Already one ordered pair is there. A comma B belongs to the relation. You have to check it. B, which implies B comma A belongs to R or not. B comma A belongs to R, that relation or not. This you have to take any one ordered pair from the relation one, but then it's opposite. That means ulta ordered pair would irrelevant. Right? A comma B iದ್ರೆ ಅದು ಉಲ್ಟಾ ಮಾಡಿದ್ರೆ B comma A ane ordered pair would iದ್ರೆ that is called as symmetric relation. A comma B belongs to relation, which implies B comma A belongs to R. For all, here A comma B belongs to the set B. A comma B belongs to set A. Clear? So reflexive means A comma A belongs to capital R. Symmetric means A comma B belongs to relation. Then you have to check it. B comma A belongs to capital R or not. In case B comma A belongs to R, then that is called the symmetric relation. It is called the symmetric relation. For example, see the example here. Example, a relation capital R in set A 1 to 3. So these all are example. Just for understanding, we are taking examples. Capital R in set A 1 to 3. Right here, for example, first example, see that capital R is equal to 1 2, then 2 1. Second one, R is equal to 1 1 2 2, then 3 2 3 2 2 3 2 1. Then see R is equal to 1 1 2 2 3 3. Observe this thing. What is the condition now? A comma B belongs to R. A comma B belongs to R. You should take any one ordered pair belongs to the relation. Then we have to check its ulta ordered pair. B comma A belongs to ordered pair or not. B comma A belongs to the relation or not. Right? So here, for example, 1 comma 2 here. 1 comma 2 is a relation. They are good here. But then even not 2 comma 1 is a 2 comma 1, so that it exists. In case you pass agile, the ordered pair is a relation agile, symmetric relation 2 comma 1 agile. Adara ella ordered pairs check ಮಾಡಬೇಕು ಮತ್ತೆ only 1 comma 2 ಅಲ್ಲ ಎಲ್ಲ ordered pairs ಆ relation ಅಲ್ಲಿ ಇದೆ ಎಲ್ಲ ordered pairs ಆ condition satisfy ಆಗಬೇಕು. For all ordered pairs satisfies this condition, then only that is called a symmetric relation. Clear? So for example 2 comma 1 ಇದು ತರಬೇಕು 2 comma 1 ಅಂದ್ರೆ 1 comma 2 ಇದೆಯಲ್ಲ, that's why it is symmetric. It is symmetric. Similarly ಇದು ನೋಡ್ರಿ doublets are always reflexive, symmetric and also transitive. 1 1 2 2 3 3 2 all. For these cases no need to check the reflexive, symmetric, transitive mode. This all passes the all doublets passes the all cases symmetric, reflexive, symmetric and also transitive. Right? Because 1 1 only ಮತ್ತೆ ಅದು ರಿವರ್ಸ್ ಮಾಡಿದ್ರೆ 1 1 ಇರ್ತದೆ, 2 2 ರಿವರ್ಸ್ ಮಾಡಿದ್ರೆ 2 2 ಇರ್ತದೆ, 3 3 3 3. Right? That's why all doublets are symmetric only. Then so that no need to check 1 1 2 2, but you have to check the 3 2 3 2 ನೋಡಿದ್ರೆ 2 3 ಇದೆಯಲ್ಲ, ರೈಟ್, ಅಂದ್ರೆ ಈ ಆರ್ಡರ್ ಪೇರ್ ಪಾಸ್ ಆಗಿದೆ ಈಗ. ನೆಕ್ಸ್ಟ್ 2 3 2 3 ಅಂದ್ರೆ 3 2 ಇಲ್ಲ ಇದೆ. ಓಕೆ, ನೆಕ್ಸ್ಟ್ 2 ಕಾಮ 1, 2 ಕಾಮ 1 ಅಂದ್ರೆ 1 ಕಾಮ 2 ಇರಬೇಕು. ಈ ರಿಲೇಶನ್ 1 ಕಾಮ 2 ಇದೆಯಾ? 1 ಕಾಮ 2 ನೋಡ್ರಿ, ನೋ. So 1 comma 2 is not there. 1 comma 2 does not belongs to relation. That's why it is not symmetric. It is not symmetric. Clear? ಎಲ್ಲ ಆರ್ಡರ್ ಬೇರು, ಈಚ್ ಅಂಡ್ ಎವ್ರಿ ಆರ್ಡರ್ ಬೇರು ಚೆಕ್ ಮಾಡಬೇಕು. ಗೊತ್ತಾಯ್ತಾ? ನೆಕ್ಸ್ಟ್ ಇಲ್ಲಿ ನೋಡ್ರಿ 1 1 2 2 3 3 ಕೊಟ್ಟಿದ್ದೀವಿ. ಡಬಲ್ಸ್ ಮೇಲೆ 1 1 1 1 ಆಗುತ್ತೆ, 2 2 2 3 3 3 3. That's why it is symmetric, right? In this case it is not a symmetric, right? So you remember the condition. Reflexive means a comma a belongs to capital R for all small a belongs to capital A. For symmetric, a comma b belongs to relation, then a b comma a also belongs to the relation capital R. Clear? So remember these two conditions. A comma b belongs to R, b comma a also belongs to relation. That is called the symmetric relation. Then third one is transitive relation. Very very important condition. Transitive, very very important and interesting relation. Transitive relation. Transitive relation. Transitive relation. Transitive relation, right? Here a relation capital R in set A if A comma B belongs to R, A comma B belongs to R, and B comma C belongs to R. That means this is the condition now. So A comma B belongs to relation and also B comma C belongs to the relation. What we want to check, which implies A comma C belongs to R or not. A comma C belongs to R. So A comma B belongs to R, B comma C belongs to R. Then A comma C belongs to R or there. Then that is called the transitive. Transitive relation. So here A comma B belongs to R, B comma C belongs to R. Hey, already makes a relational irutte. A comma B belongs to R relation, ಮತ್ತೆ B comma C belongs to R relation ಇರುತ್ತೆ. ರೈಟ್? ಈಗ ನೀವೇನ್ ಚೆಕ್ ಮಾಡಬೇಕು, A comma C ಅನೇ ಆರ್ಡರ್ ಬೇಕು ರಿಲೇಷನಲ್ ಇದೆಯಾ ಇಲ್ಲ ಅಂತ ಚೆಕ್ ಮಾಡಬೇಕು. ರೈಟ್? ಇನ್ ಕೇಸ್ A C A comma C ಅನೇ ಆರ್ಡರ್ ಬೇಕಿದ್ರೆ that is called the transitive relation. Clear? Transitive relation. Okay. For all A comma B comma C belongs to the set A. Clear? No. This is the definition of transitive relation. Then example. So the example. Here we define the relation in set A is equal to 1 2 3. Set A is equal to 1 2 3. Right? Here, for example, we have to observe an example. For example, relation is equal to 1 2 2 3. Then A comma B belongs to relation, B comma C belongs to relation. Then A comma C 1 comma 3, 1 2 2 3 belongs to relation. Then 1 3 is there or not? 1 3 belongs to relation. That's why it is transitive relation. This is one example of transitive relation here. And also you remember one more condition for transitive relation definition. One more definition for transitive. Here note, in case A comma B belongs to the relation, A comma B belongs to relation, one ordered pair in relation, but B combination B comma C does not in R. If only A comma B belongs to R, B comma C does not belongs to the relation. B comma C does not belongs to the relation. Then here no need to check the A comma C belongs to R. A comma C belongs to R. ಇದು ಇಲ್ಲ ಅಂದ್ರೆ ಏನು B comma C ಆರ್ಡರ್ ಇಲ್ಲ ಅಂದ್ರೆ ಏನು that is called the transitive relation only. R is called transitive. R is called transitive. This is the one more definition for transitive relation. Here you don't get the confusion. In case second condition is not there, then also it is transitive relation. For example, 1 comma 2, 2 combination 2 comma 3 ಇದೆ ಅಂದ್ರೆ ಇದು A comma B 1 comma 2 ಇದೇನು B comma C. ಮತ್ತೆ ಏನು ನೋಡ್ತಿದ್ರಿ ಈಗ ನೀವು A comma C ಅನ್ನು ಕಂಡೀಷನ್ ನೋಡಿದ್ರಿ A comma C ಇದೆ ಇದು ಅದಕ್ಕೋಸ್ಕರ ಟ್ರಾನ್ಸಿಟಿವ್ ಆಗಿದೆ ಇದೊಂದು ಇಲ್ಲ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ದೇ ಗಿವನ್ R is equal to only 1 comma 2, only 1 comma 2, only 1 comma 2 is given. Then here only A comma B is given. A comma B belongs to relation ಆಗಿದೆ. Then B comma C ಅనే ಕಂಡೀಷನ್ ಇದೆ ಇದರಲ್ಲಿ. B comma C is there here? No. Then B comma C ಇಲ್ಲ. B comma C is not there. Then also it is transitive. Then also it is transitive to transitive A. Then also it is called the transitive because here no need to check the A comma C also. You no need to check one. A comma B belongs to R. In case B comma C is not found here, B comma C order pair is not there, then also it is called the transitive relation. Remember that. So this is also an example of transitive relation. This is also transitive relation. Right. Take some more example. Say this is one very important one. Transitive relation. Transitive relation is very important. See some examples here. For example, we take some ordered pairs. For example, one ordered pair is capital R is equal to 1 1 2 2 3 3 3 3 1 2 1 2 2 3. This is one example, right? Next D. One more example you have to take. R is equal to 1 2 2 3 then 2 1 3 2 2 2. Right. So an example. Next one more example. One more example. R is equal to 1 1 2 2 3 1 3 3 1. See this examples. Once you have observed these examples here, for example, is it transitive or not? Is it transitive or not? See, all doublets satisfies the transitive relation. Doublets satisfies reflexive, symmetric, and also transitive. You don't need to check these cases. You have to check this case 1 comma 2. 1 comma 2 belongs to R. 1 comma 2 belongs to R one here. 1 comma 2 belongs to R. Then 2 combination here 2 2 is there, 2 comma 3 is there. So that means here 1 comma 2 belongs to R and here 2 chances is there. One is 2 comma 2. 2 comma 2 belongs to R. Then next one is 2 comma 3 belongs to R. The doublet ಆಗಿದಕ್ಕೋಸ್ಕರ no need to check the 1 comma 2 no. 1 comma 2 also is there here. Doublet is there, no need to check. Then here you want to check this condition 1 comma 2 2 comma 3. Then 1 comma 3 is there. 1 comma 3 is belongs to R or not. We have to check this condition. 1 comma 3 is there ಅದರಲ್ಲಿ. 1 comma 2 2 comma 3 is there, but 1 comma 3 is there. No, that's why it is not transitive. Clear? Similarly, second example, here 1 comma 2 is there, Then 2 comma 1. 2 comma 1 is there, 2 comma 3 is there. And also 2 comma 2. Doublet is no need to check. So 1 comma 2, second one multi condition over here. 1 comma 2, its combination is 2 comma 3 is there, and also 2 comma 1 is there. Then 1 comma 3 is there or not? 1 comma 3. I thought 1 comma 3. No. Similarly, here 1 comma 1. 1 comma 1. No. So that it is not a transitive. Similarly, here 1 comma 1, 2 comma 2, 1 comma 3. See, 1 comma 3 is there means 1 comma 3 is there means it's a combination 3 start. 3 with 3 1 is there. 3 1. Then 3 1 is there. Again 1 1. 1 1 also is there. That's why it is satisfied. This order base satisfies the transitive. Then 3 comma 1. 3 comma 1 you have to check. 3 comma 1. 3 comma 1 is there. Then 1. 1 combination of 1 comma 1 belongs to R and also 1 comma 3 belongs to R. Then 3 comma 3 is there. 3 comma 3. No, that's why it is also not transitive. It is also not transitive. Right. So this is the transitive relation examples. Right. Get the idea. Right. Last one. Just to see the definition. Last definition. Equivalence relation. Equivalence relation. Equivalence relation. So here, what is meant by equivalence relation? A relation capital R in set A is said to be equivalence when it is reflexive, symmetric and transitive. See, when the given relation is said to be equivalence relation means when the given relation is reflexive, symmetric and transitive. When the relation satisfies these three cases, just now we discussed the reflexive, symmetric and transitive conditions. When that satisfies reflexive, symmetric and transitive, that relation is called the equivalence relation. So in questions also they ask the question, show that the given relation is equivalence relation. Show that the given relation is equivalence relation. In that case, you have to check the three cases. When the given relation satisfies these three cases, then the relation is called equivalence relation. Right? Sometimes whether the given relation is reflexive, symmetric or transitive, like that cases. Check given relation is reflexive, but neither transitive, neither symmetric. Like that cases is there, questions is there in the first exercise. It will be discussed in the next class. Clear? Right. Thank you.